Okay, good morning. Assalamualaikum semua.
Good morning,
Morning,
Miss.
Miss.
Semua sihat kan ni?
Sihat.
Sehat, Miss.
Sehat Miss.
Sihat.
Sehat, Miss.
Okay, kita akan sambung our lesson. So last time we stop halfway in 5.2. So kita masih di dalam subtopik 5.2 which is induced EMF. Okay, before I continue, so last time I discuss up until first example untuk coil sahaja kan. And then example 2 dan 3 kita tidak sempat bincang, but I did tell you to attempt it on your own. So kamu ada cuba tak soalan ni? Ada yang ada cuba soalan? Soalan 2 dan 3.
Ada, Miss.
Ada masalah ke? Is there any problem with soalan 2 dan 3? I believe it's just a straightforward question. If there is no problem, I don't want to discuss this one, but kalau ada masalah, boleh bagi tahu Miss lah, so we can discuss. Yang lain? Yang lain tiada cuba lagi. Come on guys, I need your response.
Yang lain tak pasti, Miss.
Yang lain tak pasti. Yang lain masuk je lepas tu sambung tidur gitu kah? Jill sudah cuba this one. Number 2 and 3.
Miss tanya saya kan Miss?
Sorry, apa dia?
Miss panggil saya.
Sorry Jen, tak clear lah. Miss tak dengar apa yang kamu cakap. Ini type.
Ada Miss saya try buat. Tapi Miss soalan 3 saya tak dapat.
Soalan 2
Sama,
okay.
Miss.
Soalan 3 anda dapat. So I believe soalan 2 okay sebab dia sudah bagi the formula. So kamu boleh just gunakan formula yang dia bagilah. So I will skip soalan 2 ya. So kita bincang soalan 3 aja di sini. Okay, so soalan 3 di sini. It says here changing the angle between the plane of the coil and the magnetic fields. Okay, so before this, I told you there are two type of changes in coil. Either kita ubah area ataupun magnetic field. Okay, ubah angle actually it's not like it's not in your syllabus. Actually, dia boleh jadi ditanya soalan ni. But so far mesti ada jumpa lagi soalan macam ni lah. But it is possible for them to ask this kind of question sebab dia just ubah sikit je sebenarnya daripada original formula. Okay, so let's read the question here. So we have a 25-turn circular coil of wire with diameter 1 meter. It is placed with its axis along the direction of Earth's magnetic field of 50 microtesla. And then in 0.2 second, it is flipped 180 degree. An average EMF of what magnitude is generated in the coil? So here, the magnetic field and also the area is constant. Yang berubah hanyalah angle sahaja. Okay, let's write down the information that we have. So we have number of turn 25 and then diameter, and then we have the magnetic field 50 microtesla, and then time is 0.2 second. Our aim is to find the EMF. Okay, the original formula is like this, right? Negative NA cos dB cos theta dB over dt. This one kalau we have a change in magnetic field. Now we have a change in angle. So apa yang kita boleh ubah? Negative NA B cos and then d theta over dt, because our change is in terms of angle. Okay, so now we have the number of turn, area we can find using the diameter, magnetic field pun kita ada, and time pun kita ada 0.2 seconds. So angle di sini, okay, let's read first. Okay, so the coil is placed with its axis along the direction of Earth's magnetic field. Okay, let's say the Earth's magnetic field is like this. And then the axis of the coil, so dekat sini actually it's not very clear axis apa. But okay, dia bagi tahu dekat sini after 0.2 second dia flip 180 degree. So doesn't matter lah. Initially dia adalah 20 degree kah, 50 degree, 90 degree, doesn't matter. Tapi dia bagi tahu the flip here is 180 degree. Maksudnya perubahan tu adalah 180 degree. So you have to understand the sentence here. It is flip 180 degree. Maksudnya tu adalah perubahan angle. So we don't care about the initial angle. So dia sudah bagi tahu automatic, this is the change of the angle. So we know that d theta is 180 degree, and then area kita boleh cari pi over 4d square. Since we are given in terms of diameter, so bolehlah masukkan negatif tu kita boleh just ignore. Number of turn times with area, pi over 4d square. B is 50 micro. Cos 180 divided by 0.2 second. Okay, dapat berapa?
Negative 9.817 exponent negative. Exponent negative 4.
Negative 4 volt. So negatif ni kamu dapat bila kamu tekan this one kah? Cos 180, is it?
Yeah, Miss.
Yes, Miss.
Okay. So negative here we can just ignore sebab dalam soalan pun dia cakap an average EMF of what magnitude. Okay, we only need to find the magnitude. So from here, you just have to change the part here, the change in what? Kalau change in angle, so d theta. Kalau change in magnetic field, dB. Change in area, dA. So yang lain kita boleh letak di depan. Okay. So this is not in your notes actually. Memang tiadalah dibagi dalam nota kamu this formula, tapi it is possible they ask this kind of question. Okay, ada soalan so far?
So far, no question.
So far tiada.
So if the question asks change of area become dAdt and the theta become cos theta.
So kalau dia tanya change of area, negative NB cos theta, then dA over dt. Macam tu je. So cos ni kamu tidak boleh ubah ya, dia memang mesti ada. Cos ni khas untuk angle saja. So kalau perubahan angle, so cos d theta over dt. So either these three lah. These three types of changes yang dia akan tanya. Tukar soalan kamu, Jason? Menjawab soalan ke?
Okay, thank you. Thank you, Miss. Sudah.
Okay. Okay, so kalau tidak soalan, I will proceed. Okay, on how to determine the direction of the induced current. Okay, before this, I explained about induced EMF in three conductor. We have straight conductor, rotating coil, and coil. And then untuk coil, two types of changes, change of magnetic field, change of area, and also it is possible to have a change of angle. And then to straight conductor, we only have this one formula. And then untuk rotating coil, this formula, if we want to find the maximum induced EMF, we just use this one, NBA or omega. Okay, so now we want to determine the direction of the induced current for these three conductors. Okay, there are a few ways actually to find the direction of the induced current. Ada tiga cara sebenarnya, tapi misalkan aja dua aja, so that kamu, I think this one lebih senang sebenarnya untuk ajar yang dua ni daripada yang ketiga nanti. Okay, so first we use what we call as right hand palm rule. So this one berbeza dengan apa yang kita belajar dekat chapter 4. Okay, di mana untuk this one, our thumb will be the direction of the current. Fingers, okay, your finger here will be the direction of the velocity. And your palm is the direction of the field. So palm kita still direction of the field, yang berbeza adalah dua ni. Okay, so dekat chapter 4, our thumb will be the direction of the force side. So this time kita tiada force. Actually bukan tiada force, tapi kita tidak take into account that force. That's why we have current and velocity. So this one we use for straight conductor only. Okay, untuk straight conductor saja. So untuk coil ataupun straight conductor, so maksudnya straight conductor ni boleh gunakan dua method. Either this one or this one. But untuk coil ada satu saja, which is right hand grip rule. So this one kita sudah belajar dekat chapter 4, di mana your thumb will be the magnetic field and your finger will be the current. So yang ketiga ni, adalah sama macam yang kita belajar dekat chapter 4. It's the same rule. Di mana thumb will be the force, finger will be the current, your palm will be the magnetic field. And this one only apply to straight conductor. But this one needs a little bit of work. That's why I don't recommend to use this rule. So now I will only explain these two. Okay, let's see the example here for straight conductor. Okay, when we have a straight conductor, this is a straight conductor and it is placed in a uniform magnetic field. So this one uniform magnetic field lah. Di mana magnetic field dekat sini kalau X dia adalah into the page. Now initially, conductor ni adalah dekat position ni. And then we move the conductor to this position. So maksudnya when we move the conductor, obviously there is a motion, there is a velocity to this direction. So now the conductor is here. Okay. If you want to use our right hand palm rule, kita boleh terus guna, we don't need to take into account of anything. Kita boleh terus guna aja. Di mana since our punya velocity is going to the right, so your finger mesti pergi kanan. So this one gunakan tangan kanan saja, tangan kiri tidak boleh guna. So your finger going to the right, and then since this one adalah into the page, so palm kamu mesti facing down because the B is into the page. And then you will observe that direction of current adalah ke atas. Maksudnya from here to here. Okay, it is going upwards. If I label maybe this one P, this one Q. So from Q to P, the direction of the current. This is using the first right hand palm rule. Okay, this one straightforward. Ada masalah? Semua dapatkan?
Dapat, Miss.
Dapat, Miss.
Okay. Second method, we can use the right hand grip rule. Okay. Di mana your thumb will be your direction of induced magnetic field, and your finger will be the induced current. Okay. So notice here I said induced magnetic field. Induced magnetic field is the magnetic field that we need to produce. So this one adalah original magnetic field. Okay. This one needs a little bit of work here. So initially conductor ni dekat sini kan. Maksudnya area dia macam ni. Dekat part ni je. Now when we move the conductor to this position here, now dia memenuhi area dekat sini. Maksudnya the area increase. Okay, the area of the conductor increase. Okay, actually not the area of the conductor. It's the area of the when the conductor is moved, dia sapu lah area dekat sini ni. So maksudnya area increase. So apabila area increase, maksudnya flux pun akan increase because the flux is directly proportional to the area. So bila area increase, flux pun akan increase. Maksudnya magnetic field pun akan increase. But in this case, kita punya magnetic field adalah uniform. Okay, apabila flux increase, okay, according to Lenz law, sebab Lenz law cakap, we need to oppose the change. Maksudnya there is a change here. So Lenz law cakap, we need to oppose the change. How can we oppose the change? So since area increase, kita mau ubah kan? Kita mau tentang perubahan tu. So maksudnya sekarang ni, our aim is to decrease the flux. Okay, we need to decrease the flux. How can we decrease the flux? Okay, Lenz law cakap, we need to produce another magnetic field. Okay, we need to produce another magnetic field that is opposite direction. So, initially dia adalah into the page. So kalau opposite direction, dia mesti out of the page. Now, the magnetic field induced is out of the page. So your thumb must be going upwards, not upwards like coming out of the page lah. So kamu buat your thumb macam ni. And then you notice that your finger will be going this way, which is anti-clockwise. Okay, dia adalah anti-clockwise macam ni. Okay, semua buat ya. So when your finger that represent the current is anti-clockwise, maksudnya this is the loop. Maksudnya your direction of the current will be like this. It is anti-clockwise. So samalah. Kamu akan dapat benda yang sama macam kita gunakan right hand palm rule from here to here. But for conductor, okay, kita tidak boleh tulis anti-clockwise. We need to be more specific. Selalunya soalan dia akan label dekat sini. So if it's QP, then you can say it is going upwards because you want to find the direction of the current on the conductor. Okay, mesti dekat conductor. That's why we need to be specific. So the current will flow from Q to P. Let me write down here. I induce is from Q to P. Okay, because kenapa kita perlu hasilkan magnetic field yang di opposite direction? Okay, sekarang ni magnetic field kita sangat banyak kan? Dan kita mau kurangkan dia, mestilah kita kena tentang. Maksudnya kalau kita dia mesti cancel this magnetic field. That's why untuk cancel magnetic field ni, it must be in the opposite direction. So kalau opposite now, our magnetic field will be out of the page. Boleh faham kan di situ?
Boleh, Miss.
So far boleh, Miss.
Okay, so untuk yang first, kita terus guna je because we have the velocity, we have the current and the pump. Apa yang kita nampak dekat situ tu adalah the direction of the magnetic field. But untuk right hand grip rule, we need to determine first whether the area dia increase ataupun tidak. So kalau increase, it must be in the opposite direction. Maksudnya we want to decrease that flux. So the B induced must be in the opposite direction. So your thumb here is the direction of the B induced, not the original one. Okay, let's see another example here. Okay, so here we have the magnetic field out of the page. So ini adalah out of the page. Initially dia dekat sini and then we move it to here. So initially dia memenuhi ruang ni. And then bila kita ubah dia ke sini, now ruang dia semakin kecil lah. Meaning that the area decrease. So bila area decrease, flux pun akan decrease. Now bila flux decrease, we need to increase that flux. Okay, flux dekat sini ni kita perlu increasekan because original dia macam ni kan, original dia macam ni and now we only have this magnetic field. So in order to increase the flux, macam mana kita mau increase? Do we need the magnetic field out of the page? Into the page?
No, Miss.
Out of the page.
Dia mesti out of the page. Sebab sekarang ni, okay, kamu tengok titik-titik ni kan, bulat-bulat ni sebagai bilangan magnetic field lah. Kita assume dia adalah bilangan magnetic field. Now, bilangan magnetic field dekat sini nampak ada banyak kan? And then bila kita ubah, magnetic field dia jadi sikit. So kita mau tambah magnetic field tu. So mau tambah, kenalah same direction. Kita kena tambah lagi tu bulat-bulat lah. So that the magnetic field will increase. So here, when the flux decrease, we want to increase the flux. Therefore, the induced magnetic field must be in the same direction. So same direction, original macam ni. Same direction will be out of the page juga lah. So when your thumb is out of the page, you will see that your current induced will be going this way. So maksudnya dia adalah anti-clockwise macam ni. So samalah. It will be like this. So the induced current will be anti-clockwise. Let's say here P, this one Q. Induced current is from Q to P. And if we want to use the right hand pump rule, so your velocity is going to the left. So your finger, okay, mesti pergi kiri and then this one is out of the page. So your palm is facing upward, facing up. And then you will notice that your current is going upward. Okay, going upward like that. So depends pada kamu which one yang kamu rasa lebih senang untuk kamu gunakan. Kedua-duanya adalah betul lah. Dua-duanya kita boleh gunakan. Either this one or this one. But you have to always remember if we are using this one, we need to take into account the change in the area here. Any questions so far?
Miss, I have
No,
question.
Miss.
Apa dia, Brian?
Yang using right hand grip rule tu kan, kalau thumb dia tu point upward maksudnya out of the page, and kalau thumb dia point downward maksudnya into the page.
Yes. Dia macam
Okay.
your thumb is masuk dalam kertas kan. That's why kita punya thumb mesti ke bawah. So that will be into the page.
Okay, Miss.
Okay. Any other question before I proceed to the next one?
No question, Miss.
Okay. Next one kita tengok untuk circular coil ataupun rectangular coil. As long as dia coil lah. So boleh jadi dalam soalan kamu dia adalah rectangular, boleh jadi dia adalah circular. Okay. So circular coil kita akan gunakan right hand grip rule sahaja. Okay, tidak boleh gunakan palm lah dekat sini. Okay, so this one is when we have a change in magnetic field. Okay, initially the coil is placed in a uniform magnetic field and then we move it to another place di mana dekat sini we don't have magnetic field. So maksudnya magnetic field dekat sini decrease. Initially dia di sini and then we move it to this place here where there is no magnetic field. So when the magnetic field decrease, maksudnya flux pun akan decrease. And we want to increase that flux. Maksudnya original dia adalah macam ni kan. Maybe ada, okay, original dia ada empat titik di sini, 4 magnetic flux, contohlah. And then we want to increase that flux, maksudnya kita kena tambah the same flux, the same magnetic field. That's why apabila flux decrease, the direction of the magnetic field will always be in the same direction. So bila same direction, this one adalah into the page. So your thumb pointing downward, and then you will notice that your finger is going clockwise. Is it clockwise? Yes. So your finger will be clockwise. Maksudnya dia akan macam ni, the direction of the current. So you can label here the direction of the current. Boleh?
Boleh, Miss.
Boleh, Miss.
Okay, this one is when we have the change in magnetic field. Okay, this one sama juga, change in magnetic field. Okay, so tadi tu kita boleh nampak dengan lebih jelas kan magnetic field dia. Daripada ada, we move it to a place there's no magnetic field. Okay, so now we have the magnetic field, but initially, okay, jumlah magnetic field yang memenuhi coil ni ada 4 je from here. And then we move it to a place with higher magnetic field, stronger magnetic field. So dekat dalam coil ni, we can see that, okay, ada banyak sudah kan jumlah magnetic field yang memenuhi coil. So from here, actually, the flux will increase. So apabila flux increase, we want to decrease that flux. So how can we decrease that flux? Kita kena tambah magnetic field yang opposite direction. So dekat sini into the page, now opposite direction out of the page. So your thumb will be pointing upward and then you will notice that your current induced is going anti-clockwise. Okay, actually dekat sini mesti tulis. So your current will flow anti-clockwise direction. Maksudnya macam ni lah kan? Is it? So that will be the direction of your current. Okay, untuk coil kita boleh gunakan clockwise ataupun anti-clockwise. Sebab memang macam tu je lah dia punya direction kan. There is no upwards or downwards. Okay, so this one is for the change in the magnetic field. Okay, next one, when we have the change in area. So change in area berlaku apabila kalau ada keyword dekat dalam soalan tu, dia either cakap it is being stretched ataupun being compressed, I think. Okay, usually, okay, kalau dia cakap being stretched tu, dia akan tulislah stretched to what value. So daripada value tu kamu boleh tengoklah adakah dia increase ataupun decrease. So in this situation, we have the same magnetic field. Magnetic field still sama, dia masih diletakkan di magnetic field yang sama, yang uniform. And then initially dia macam ni and then it is being compressed, dia dikecilkan. So now the area is smaller than the original one. So apabila area smaller, kita punya magnetic field yang memenuhi area tu pun akan jadi sikit. And then sama juga, konsep yang sama kita gunakan. When the area decrease, magnetic flux pun decrease. Now we want to add more flux. So when we want to add more flux, kita kena tambah magnetic field yang ada di direction yang sama. So the magnetic field must be in the same direction. So bila same direction, this one is into the patch, right? So your thumb will be pointing downwards. Okay, this one Mr. lukis tangan, tapi kamu boleh buat. So pointing downwards, so your current will be like this, clockwise, right? So your current will be clockwise. Okay. And then for this one, okay, dia daripada kecil jadi besar lah. This one, the area increase. When the area increase, we want to decrease that magnetic field. So we add a magnetic field that is in opposite direction. So in opposite direction, your thumb must be pointing upwards, which is out of the page. And then you will see that the direction of the the direction of the current will be anti-clockwise macam ni. Okay, semua dapat?
Dapat, Miss.
Dapat
Ada
Miss.
soalan so far?
So far, okay, Miss.
So far okay. Okay, so kalau okay, let's look at the example. So this is the first example here for the straight conductor. Okay, we are given here a 20 centimeter long metal rod CD is moved at speed 25 meter per second across a uniform magnetic field of flux density 250 millitesla. The motion of the rod is perpendicular to the magnetic field as shown in figure. So we have here the rod CD, dia sudah dia sudah label, and then we have the uniform magnetic field. So magnetic field di sini kalau dot dia adalah out of the page. So magnetic field here is out of the page. Okay, first question, calculate the motional induced EMF in the rod. So what we want is induced EMF. Okay, what is the what is the formula for the induced EMF untuk straight conductor? Someone can tell me what is the formula?
BLV sin theta.
Apa dia? BLV
Sin theta.
sin theta. Okay, thank you. So there is only one formula untuk straight conductor, BLV sin theta. So untuk kamu kenal pasti, adakah formula untuk straight conductor? Usually dia akan bagi the length here. Okay, untuk coil dia akan bagi area. Okay, there will be area in that formula instead of the length. Usually kalau kamu tidak ingatlah sebab banyak sangat formula kan. Walaupun ada dibagi list of formula tapi dia tidak bagi tahu formula ni untuk apa. Adakah untuk conductor, adakah untuk coil ataupun solenoid. Okay, so here when we have the length, meaning that it is for something yang ada value for length lah, which is conductor. Okay, so here we want to find E. We are given the value for L. So this is the value for L, the length 20 centimeter, and we are also given the speed 25 meter per second, and also the value for magnetic field. Okay, semua kita ada, BLV kita ada. Now the angle here will be, what is the angle? Angle must be angle between V and B. What is the angle between the velocity and the magnetic field here?
90 degree.
Okay, 90 degree. Sebab kita punya V macam ni kan. And then your magnetic field, dia upward. Dia out of the page. So boleh nampaklah dekat situ dia adalah 90 degree. So you just masukkan 250 millitesla. Okay, don't forget the milli there. And then it is in centimeter. The length is in centimeter. So convert to meter. Then sin 90.
$1.25 volt.
1.25 volt. Okay, next one. If the rod is connected in series to the resistor of resistance 15 ohm, determine the induced current and its direction and the total charge passing through the resistor in 2 minutes. Okay, so now kita punya conductor ni connected in series with a resistor. Okay, let's see. This is the magnetic field. And this is the conductor. Since the motion of conductor is going to the left. Now conductor ni akan connected in series with a resistor. So maksudnya, we have another resistor here. We connect it to a resistor as long as it is in series lah. Kalau dekat sini pun sama jugalah, still in series. And this resistor has a resistance of 15, is it 15? Yes, 15 ohm. Now we want to find what is the induced current and its direction. So first we want to find induced current and direction. Okay, let's find the direction first. Okay, which way is the direction of the induced current? Okay, using the method that I explained just now, can you figure out which way is the direction of the induced current?
From D to C.
From D to C. Okay, if you use your right hand palm rule, so your finger will be pointing to the left. And then since this one adalah out of the page, so kamu punya palm mesti di atas, menghadap kamu lah. And then you can see that your direction of thumb will be going upward. So maksudnya the direction of that current will be D to C. I induce flows from D to C. Okay, next one, we find the magnitude of the induced current. So how do we find this magnitude of induced current? Which formula can we use? Anyone? Anyone ada idea which
V
formula?
equals to IR.
V equals to O. Okay.
V is equal to IR. So we can use Ohm's law. Since here, dia mau adalah induced current. So maksudnya V di sini adalah induced EMF. So induced EMF kita sudah ada. And then resistance pun kita sudah dibagi. So you can just use this Ohm's law. 1.25 equal to I times with resistance. I will be equal to
at point 0.33.
0.33 ampere.
Exponent negative 2.
Exponent negative
2
2
ampere.
ampere. Okay, next one, determine the total charge passing through the resistor in 2 minutes. So next one, we want to find Q, the total charge. What is the formula we can use to find this Q?
Q equals to IT.
Q equal to IT, di mana T dia sudah bagi adalah 2 minutes. So I kita sudah ada at 0.33 exponent negative 3, and then T must be in seconds, so ubah kepada second lah. And then you will get Q is equal to
Coulomb.
10,
9,
9, only 9,
9.99, Miss.
9.99 Coulomb. Jawapan berapa? Jawapan 10. Okay, if you leave your answer as 10 Coulomb pun boleh. 9.99 pun boleh juga. Okay, ada soalan so far?
so far tiada, Miss.
So
Ada,
far
Miss.
tidak.
Miss.
Okay, kalau Miss laju sangat, bagi tahu ya. Can I proceed to the next example?
Yes, Miss.
Boleh, Miss.
Okay, next example here, example 7. Okay, still for stirred conductor. Okay, we are given the conductor here placed in a uniform magnetic field. So consider the R is equal to 6 ohm, the length of the conductor 1.2 meter, the magnetic field is uniform 2.5, directed into the page, as you can see here. Now we want to find at what speed should the bar be moved to produce a current of 0.5 in the resistor, and what is the direction of the induced current. Okay, so initially kalau kita nampak this one B, this one A, initially the conductor is here, and then it is moved here to the right. Now we want to find what speed, what is the velocity, so that the current produced will be 0.5 ampere, given that the resistance, the length, and the magnetic field. Okay, using the same formula kita tadi adalah E is equal to BLV sin theta. Now our M is to find E. Okay, we have B, this one is B. Length is also given, and angle dekat sini will always be 90 degree. Okay, angle selalunya akan jadi 90 degree lah. From here you can always tell that okay, V pergi kanan, and then your magnetic field into the page. So dia mesti 90 degree. Okay, so in order to find V, we need to find E here. And since we already given I, so bolehlah masukkan dekat sini, IR is equal to B LV sin theta. Kalau mau cari satu-satu dulu pun boleh. Buat macam ni terus pun boleh juga. As long as kamu start with writing down the original formula. So I 0.5, resistance 6, B is 2.5, length 1.2, V sin 90. So we can get that the velocity will be equal to
1 ms negative
1 meter per second. Semua dapat?
Dapat, Miss.
Dapat, Miss.
Dapat, Miss.
Okay. Next one, we want to find what is the direction of the induced current. Okay, cuba buat dulu which way is the direction of the induced current.
From B to A.
From B to A, going upward. Okay, semua kena cuba ya. So the direction of induced current, induced um, flows upward from B to A. Okay, any question?
So
No,
far,
Miss.
Okay, tiada soalan. Let's continue to the next one. Okay, next one, example 8. So this one is for coil. Okay, here we have the flexible loop with radius 12 centimeter, and its magnetic field is 0.15 Tesla. So this is the coil, the loop is placed in a uniform magnetic field 0.15 Tesla. The loop is grasped at point A and B and stretched until its area is nearly zero. If it takes 0.2 seconds to close the loop, find the magnitude of the average induced EMF during this time. Okay, so here, daripada perkataan ni, dia sudah cakapkan, it is stretched until its area is nearly zero. So, maksudnya perubahan yang berlaku di sini adalah perubahan area. So, initially, okay, we have some sort of area, some value of area, and then final dia adalah kosong. So we want to find E induced. So using the formula di mana B is constant, E is equal to negative NB cos theta dA over dt. Okay, so this one straightforward juga. What is the number of turn here? Are we given the number of turn?
No, Miss.
No, we are not given the number of turn. So if we are not given the number of turn, we can always assume it is 1. Okay, only one loop. Sahajalah. So number of turn is 1. Magnetic field. And then what is the angle here? What is the angle of the between the area and the magnetic field?
90 degree kan, Miss?
90 degree. Are you sure? 90 degree?
Tak tahu.
Dah tahu. Okay, kalau kita tengok kan. Okay, this one dia berbeza dengan conductor ya. Okay, magnetic field kita ni into the page kan. Okay, kalau Miss lukis macam ni lah Miss lukis. Dia macam into the page lah. And then kita punya loop tu kita letak di bawah. Macam ni. Okay, so this is the amount of magnetic field yang masuk dalam loop. And then area of the loop must be always perpendicular to the plane. So ni adalah loop, ni adalah area. Okay, they must be always perpendicular. So from here we can see that the angle between B and A is equal to 0. Okay, dia berbeza dengan straight conductor. Okay, so the change in area will be final minus initial. So final dia kosong, initial. Okay, initial dekat sini pi r square. So area is pi r square. Radius kita 12 cm, so ubah kepada meter. Divided by the time taken, 0.2 second. And then you will get the induced EMF is equal to
Miss.
Negative.
Negative. Negatif apa?
Miss, saya dapat 0.034 je. Dia ada negatif.
0.034 volt. Okay, negatif ni we can just ignore actually. Sebab memang kita akan ada negatif dekat depan kan. The original formula memang ada negatif. Sebab negatif ni just to indicate that Lenz law tu cakap direction must be to oppose the change. So usually negative we can just ignore. Kalau nak tulis negatif pun tak apa. Memang kita selalu guna voltage ni 0.034. So voltage untuk chapter 5 dia nak kisah positif or negatif. Tapi dekat chapter 6 nanti dia akan ada value lah. Kita akan take into account that voltage. But chapter 5 voltage ni positif negatif just to indicate the direction only. Okay. So if you leave your answer like this ataupun letak negatif pun boleh. Okay, semua dapat 0.034 volt.
Dapat, Miss.
Okay. Let's see the next example. So this one example untuk rotating coil for generator. So tadi kita sudah tengok straight conductor and also coil. Now we look at the rotating coil. Okay, so we are given an AC generator consists of 8 turns of wire. Given that the area is 0.09 meters square, the total resistance of the wire is 12 ohm. The loop rotates in 0.5 Tesla magnetic field at a constant frequency of 60 Hz. Find the maximum induced EMF. Okay, so we are given here the number of turns and then area, the resistance, and also we are given frequency. Okay, we are given frequency since this one adalah rotating coil, coil yang sentiasa rotates. That's why we have the frequency. Now first question, we want to find maximum induced EMF. Okay, remember what is the formula of the maximum induced EMF?
NBAW.
NBA omega. Okay, kita tidak perlu tambah sign di belakang. Okay, because at maximum, the angle is equal to 90 degree. Okay, so here we have the number of turn, B pun ada. Are we given the B? Or this one? Okay, I forgot to write it down. B 0.5 Tesla. Area is given and omega, we can find it using the frequency. So what is the formula for omega?
2 pi F.
2 pi F, right? Okay, so boleh masukkan information ni semua. Make sure all of the information are in SI unit. So we can get maximum induced EMF will be equal to,
Miss,
yes,
yang number of turns tu bukan 8 kah?
oh sorry, dari mana pula datang 25 eh? Okay, add.
$135.72 volt.
134.725.
35 miss.
135. 135 volt. Is it
135.72 volt.
7.72 volt?
Yeah, Miss.
Okay, and next one, we have to find what is the maximum induced current. So maximum induced current maksudnya kita boleh gunakan the value for maximum induced EMF. So gunakan Ohm's law, E max is equal to I max times with R. 135.72. Resistance is 12 ohm, so you can get the maximum induced current is equal to
11.31 ampere.
11.31 ampere. Okay, so here jangan letak I max lah, kita letak I induce. Okay, semua dapat 11.31, and then this one 135.72.
Dapat, Miss. Dapat, Miss.
Okay, the question is very straightforward actually. Because sini you just gunakan formula. So banyak soalan dalam chapter 5 ni adalah gunakan formula sahaja actually. Part untuk explanation yang akan ada susah sikit lah untuk kamu explain. So this one part untuk soalan UPS nanti. So soalan UPS kamu akan expect dia banyak tanya soalan konsep. That's why Miss still bagi jugalah penjelasan in detail about the concept. So boleh jadi dekat dalam soalan UPS banyak yang Miss nampak lah before this, not sure yang this time. So before this dia banyak tanya pasal direction actually. So you need to know how to use your hands to find the direction. Okay, mostly dia tanya direction of the current or direction of the force. That one for chapter 4 lah. So untuk calculation, I don't think there is any problem sebab dia macam straightforward sahaja untuk chapter 5. Okay, kita tengok the next example here. So we have another 2 example untuk 5.2. Okay, so the next example is still under the generator and under the rotating coil. Okay, so here we are given an automobile generator produce 12 volt when turning at 500 revolution per minute. What potential difference will it produce at 1,200 revolution per minute? Okay, we are given that the generator produce EMF of 12 volt when the angular frequency is 500 revolution per minute. And now what we want is what is the potential difference it produces when the angular frequency is 1,200 revolution per minute. Okay, so how can we find this one? Ada sesiapa yang ada idea how to solve this kind of question? If we are only given
Ratio ke, Miss?
okay, we can use ratio. So if we are only given 2 information, and as you can see here, it's more on comparison kan. So dia macam perbandingan. So bila kita nampak macam perbandingan, we can use in terms of ratio. Okay, so the original formula is E is equal to NB omega sine theta, right? So from here you can see that EMF is directly proportional to omega. So kita boleh cakap, okay, let's label this one E1 omega 1, E2 omega 2. So E1 divided by E2 is equal to omega 1 divided by omega 2. So our M is to find E2. So you just masukkanlah 12 bahagi E2, 500 bahagi 1200. Dan kamu akan dapat E2 will be equal to
28.8 volt.
20,
28.8.
28.8 volt. Okay, so here, do we need to change the unit?
No need.
Okay, we don't need to change the unit here. Although the unit is not in SI unit, tapi in the end bila kita buat ratio, we can just cancel that unit. So tidak perlulah kamu susah-susah untuk ubah unit ni kepada radian per second. If it is in terms of ratio, sebab in the end kita akan cancel that unit. Okay, ada soalan for this question?
No, Miss.
Okay, last example. Okay, we have a rectangular coil of 100 turns with dimension of 10 centimeter times 15 centimeter. It rotates at angular velocity of 200 RPM in a uniform magnetic flux density 5 Tesla. Calculate the maximum EMF produced by the coil. So this one, we have a keyword here, it rotates. So this one adalah for generator. Okay, we are given number of turns, 100. And then area dekat sini, we are given dimension. So we can calculate that one. 10 times 15 centimeter square. So kamu akan dapat 150, I think. 150 exponent negative 4 meter square. Betul kah? Ubah kepada meter square. And then velocity, angular velocity 200 RPM. And magnetic flux density 5 Tesla. Now first we want to find maximum induced EMF. So again, maximum induced EMF is NBA omega. So we have N, B kita ada, 5 Tesla. Area also we are given here. And then omega pun kita ada. Okay, but omega here is not in SI unit. So you need to convert this one to SI unit. Okay, convert dulu. Okay, convert kepada radian per second, kamu dapat berapa? Masih ingat lagi macam mana mau convert?
3.33 kah?
Berapa dia? 3
33 kah?
No. Macam mana kamu convert? Revolution per minute to radian per second.
Two pi over 60 dalam radian mode.
Can you give me in terms of decimal?
Jawapannya kah, Miss?
Ada jawapannya? Okay, Miss nak bagi dulu jawapan. 20?
20.94.
20.94. Okay, macam mana kamu dapat 20.94 ni?
200 darab 2 pi over 60 dalam mode radian.
Okay, 200 darab dengan 2 pi over 60. Okay, so kalau kamu dah ingatkan macam mana, adakah kita kena darab 2 pi over 60 ataupun 60 over 2 pi. So, kita tengok kita punya unit di sini. So, our unit is revolution per minute and we want to change it to radian per second. So 1 revolution bersamaan dengan berapa radian? 1 pusingan lengkap bersamaan dengan 2 pi, right? 1 complete cycle is equal to 2 pi. And then 1 minute is equal to 60 second. That is why we need to darab dengan 2 pi over 60. Benda ni kamu tidak perlu ingat pun sebenarnya. Kamu just tengok je unit and then we want to convert to what unit. If we want to convert, kadang-kadang ada soalan dia bagi revolution per second. Dia terus bagi revolution per second. So kalau revolution per second, kamu just darab dengan 2 pi sahaja. Tidak perlu bahagi 60 lagi. Okay, so you have to see that unit there. Okay, so always kena ingat this unit conversion, dia tidak bagi dalam formula. Kamu mesti kena tahu how to convert this unit. Okay, make sure semua dapat 20.94 radian per second. So you leave your answer in terms of decimal. And then you just masukkan N is 100, B is 5 Tesla, area 150, and then omega 20.94. So maximum induced EMF is equal to
157.05 volt.
157.05 volt. Okay, semua dapat 157.05 volt.
Dapat, Miss.
Okay, next one, we want to calculate the induced EMF at the instant when the plane of the coil makes an angle of 38 degree to the magnetic field. Okay, tadi kita kira maximum induced EMF. Now we want to find what is the induced EMF apabila plane of the coil makes 38 degree to the magnetic field. Okay, so let's say this is the magnetic field and we have the plane of the coil like this, and then angle between them is 38 degree. So here, using the formula E is equal to NBA omega sine theta, right? Is it sine theta? Yes. And then angle dekat sini must be the angle between B and A. Okay, again, angle between B and A. So what is the angle between B and A here? How can we find the
52 ke, Miss?
52. So macam mana kamu dapat 52?
90 minus 38.
90 minus 38. So kamu akan dapat 52 because we want to find the angle between this is area kan. Area ni sentiasa 90 degree to the plane. So we want to find angle between area and magnetic field, this one here. That's why 90 minus 38, so kita akan dapat 52 degree. Okay, and then the rest you just masukkan area yang area sama juga 150 times with omega and then sine 52.
$133.7 6.
123.76.
123.76.
Okay, 123.76. Semua dapat this value?
Dapat,
Dapat,
Miss.
Miss.
Dapat,
Dapat.
Miss.
Okay, ada soalan so far? Untuk 5.2?
So far clear, Miss.
Okay, so far clear. Okay, so this one is last example. Okay, before we continue to the next subtopic, okay, let's go through again what we learned in 5.2. Okay, so dalam 5.2, we learn about induced EMF. How can we produce induced EMF? Okay, induced EMF kita akan apply dua laws, Faraday's law and Lenz's law. Di mana Faraday's law dia cakap tentang magnitude of the induced EMF, and then Lenz's law dia cakap pasal direction. So how can we produce this Faraday's law? Bukan Faraday's law. How can we produce this induced EMF? Tanpa menggunakan battery, because in order to have EMF we need to have battery, right? That's what we learned previously in chapter 3. Okay, now we want to produce that EMF without connecting to a battery. So what we do is we have a magnet. Okay, we have a magnet, we place it next to a coil ataupun solenoid. So this one here is solenoid, ataupun kita boleh gunakan coil lah, coil yang ada banyak turn. So we place the magnet. Okay, magnet ni kita akan, the keyword here, the magnet must be constantly moving. Dia tidak boleh kita just letak and then terhasilnya induced EMF. No, the keyword here, the magnet must always move. Okay, dia mesti ada some kind of movement. So that bila ada some kind of movement, we can change the magnetic field here. So when we change the magnetic field, we actually changing the magnetic flux. So according to Faraday's law, when there is a change in magnetic flux, we can induce EMF. Therefore, there is a current induced flowing through the circuit. So depends kepada pergerakan magnet. Kita boleh tengok, kita boleh tentukan the direction of the current here. So we have two cases apabila current magnet mendekati and then apabila magnet menjauhi. Okay. And then we also learn how to find the induced EMF in 3 types of conductor. We have straight conductor, rotating coil, and also coil here. So there are only 2 types of changing. Either we change the magnetic field ataupun we change the area. And then we have 2 types of ways to find the direction of the induced current. Untuk straight conductor, kita boleh either gunakan right hand palm rule ataupun right hand grip rule. So depends kepada situation lah mana satu yang kamu mau gunakan. Kedua-duanya kita boleh gunakan. Dan untuk coil kita hanya ada satu saja, right hand grip rule. Okay, so that one is in 5.3. Okay, we learn how to produce, well, actually not how to produce. Okay, we learn how magnet can produce the the induced EMF. Okay, so now kita masuk kepada the next subtopic. It is self-inductance. Okay, dalam self-inductance, our aim is still the same. We want to find how can we produce induced EMF. So this time, kita akan produce induced EMF by changing the current. Okay, we want to produce EMF by changing the current. So we learned in chapter 4 that current, when there is a conductor carrying a current, this conductor will produce a magnetic field. So current can produce magnetic field, and then in 5.2, magnetic field can produce current. Now, we want to produce E induced here by changing the current. So, if we want to change the current, maksudnya dalam kita punya circuit, mesti ada sudah current tu. So, how can we do this? Okay, we have a solenoid. So, this is a solenoid. We have a few number of turns of the wire here. And then we connect with a switch, with a battery, and with a resistor. So, resistor yang kita gunakan dekat sini adalah variable resistor, di mana kita boleh ubah resistor ni. Okay, so when we connect the switch, maksudnya kita punya circuit sudah complete, obviously there will be a current flowing in the circuit. So current tu dia akan flow in, ikutlah, so this one positive, right? So maksudnya daripada sini, then ke sini. So this, for now, in this situation, the direction of current is from here to here. Okay, so now we want, we learn that when there is a current, there is a magnetic field. So maksudnya, originally, circuit ni dia ada magnetic field dia. Okay, dia ada magnetic field dia. So macam mana kita mau tentukan magnetic field tu? Okay, gunakan right hand grip rule, di mana your finger will be the direction of the current, your thumb will be the direction of the north. So from here, kamu boleh nampak kan, current tu dia lalu belakang. So your thumb will be pointing to the right. Maksudnya sebelah kanan tu adalah north, sebelah kiri adalah south. So this is the original circuit. Okay, we haven't changed anything yet. Okay, kita connect dengan battery, dengan resistor, and then ada current lalu. So apabila ada current, obviously akan ada magnetic field. Now, we want to induce EMF. Walaupun originally dia ada EMF kan dekat sini. So we want to induce another EMF. So how can we induce another EMF? We do it by changing the current. So how can we change the current? We change the resistor. So as I said earlier, resistor ni, since dia adalah variable resistor, kita boleh ubah dia. Kita boleh tune resistor ni. So here, kita ada dua case, when we increase the current and when we decrease the current. Okay, case yang pertama is when we increase the current. Okay, since Ohm's law kata V is equal to IR, so I is directly inversely proportional to the resistance. So in order to increase the current, we need to decrease the resistance. So when we decrease the resistance, current pun akan increase. Apabila ada perubahan current, obviously akan ada perubahan magnetic field sebab originally dia ada magnetic field kan di sini. So magnetic field pun berubah. And then apabila ada perubahan magnetic field, akan ada perubahan magnetic flux. Okay, so delta here to indicate perubahannya. So akan ada perubahan magnetic flux. And then we learn in 5.2, apabila ada perubahan magnetic flux, we will produce induced EMF. Okay, akan terhasilnya induced EMF here. So maksudnya dekat sini akan ada EMF, and then akan ada juga induced EMF, di mana kita panggil dia sebagai back EMF. So the direction of the back EMF here, we can determine. Okay, dia punya konsep sama macam yang tadi. Okay, apabila flux increase, we want to decrease the flux, right? So if we want to decrease the flux, maksudnya the magnetic field must be in the opposite direction. Ni sama konsep macam tadi ya, Miss explain pasal coil tu. Our aim here is to decrease the flux. So in order to decrease the flux, the magnetic field must be in opposite direction. So originally magnetic field tu dia macam ni kan, from N to S. Ni adalah direction of the magnetic field. So maksudnya daripada sini ke sinilah, ni adalah the magnetic field. Now we want to decrease the flux, it has to be in the opposite direction. So kalau opposite direction, dia akan jadi macam ni lah. That's why Miss sudah lukis dekat sini. The direction of the induced EMF ataupun nama lain dia adalah back EMF adalah going to the right. So kalau going to the right, meaning that dekat sini akan jadi N, dekat sini akan jadi S. So apabila di sini N, dekat sini S, direction of current kita pun akan berubah. Direction of current pun akan jadi opposite. Okay, boleh faham proses dia di sini?
Boleh lah, Miss.
Yang lain?
Sedang cuba faham, Miss.
Apa dia, Brian?
Sedang cuba faham.
Sedang cuba faham. Okay. Okay, Miss ulang sekali lagi ya. Okay, so here, in self-inductance, okay, di dalam self-inductance, our aim is to produce EMF. How can we produce EMF? Dia berbeza dengan 5.2. 5.2 kita produce by changing a magnet, placing a magnet. Okay, kita gunakan magnet. But now, kita tidak gunakan magnet. Kita gunakan circuit sahaja. Dan macam mana kita cara untuk produce induce ni, kita akan change the current. Okay. How can we change the current? We use the resistance. So if we want the current to increase, resistance kita mesti decrease. Sebab Ohm's law kata current is this. So Ohm's law kata current is inversely proportional to the resistance. So kalau resistance rendah, current akan jadi tinggi. So because we want current to increase, we need to decrease the resistance. So bila current increase, maksudnya ada perubahan current. Apabila ada perubahan current, akan ada perubahan magnetic field. Apabila ada perubahan magnetic field, flux pun akan berubah. So kita increase current, yang lain semua akan jadi increase. In 5.2, Faraday's law kata apabila ada perubahan flux, EMF akan terhasil. Okay, ni Faraday's law yang cakap. Apabila ada perubahan flux, EMF akan terhasil. And then, since Lenz's law cakap, kalau ada perubahan, dia mesti oppose. Okay, dia mesti oppose that changes. So, how can we oppose? For this type of situation, since dia increase kan, so apabila dia increase, kita mau oppose, kita mau jadikan dia decrease pula. So apabila kita mau jadikan dia decrease, B tu mesti opposite direction. Okay, untuk dia cancel, dia counter back that EMF. EMF yang original adalah from north to south. Ni yang original. And then dia mau tentangkan perubahan tu. So dia mau counter back, dia mestilah opposite direction. So that opposite direction, we call it as back EMF. So maksudnya dekat dalam circuit ni kita ada dua magnetic field. Satu daripada sini ke sini, ni yang original. Sebelum kita ubah current tu. And then lepas kita sudah ubah, magnetic field tu daripada sini ke sini. Boleh? This is Miss lukis in terms of yang senang lah di sini. Dia punya proses. First kita decrease current so that, first kita decrease resistance so that current akan increase. So apabila current increase, ada perubahan magnetic field dan juga magnetic flux. So apabila ada perubahan, Faraday's law kata kita akan dapat hasilkan induced EMF. Okay, ada soalan so far?
Miss cakap ada dua magnetic field.
Yes.
Jadi kalau saya letak serbuk besi nampak dua corak lah tu.
Kalau letak apa dia?
Serbuk besi dekat anu tu nampak dua corak.
Sorry, Miss tak jelas lah apa yang kamu cakap. Letakkan.
Kalau letak serbuk besi dekat kasih tabur situ jadi nampak dia membentuk dua corak Miss.
Actually
Sebab ada
tidak.
dua magnetic field.
Actually tidak, dia akan berubah tu. Originally kita akan nampak satu corak dulu from here to here, and then as we change the resistance, corak tu pun akan mula berubah. Sebab dia mau oppose the changes, right? So dia akan mula berubah. So nanti kita akan nampak macam ni. I don't think there is two corak in one setup. But
Oh, faham Miss.
tapi Miss rasa memang macam tu lah dia punya konsep. Tidak boleh lah ada dua rasanya. Sebab current ni kita tidak boleh ada dua direction juga. Initially dia macam ni je. Okay, initially dia macam ni and then kita ubah barulah current tu akan lalu opposite direction. Boleh?
Boleh, Miss.
Okay, I know it's
Boleh,
difficult
Miss.
to understand this one. Dapat, kita continue dulu. Okay, kita continue. Next one is when the current decrease. So, bila case kita mau decrease current, resistance kita akan increase kan. So, apabila kita increase current, apabila kita increase resistance, current akan decrease. So, apabila current decrease, magnetic field pun akan decrease and then flux pun akan decrease. Now, our aim is to increase the flux. Okay, to increase the flux. So how can we increase the flux? We need more magnetic field in the same direction. Konsep yang sama dengan yang Miss explain tadi. When we want to increase the flux, more magnetic field, we want to add more magnetic field. So in order to add more magnetic field, it has to be in the same direction. So original dia macam ni. And then magnetic field is from this north to south. So kita kurangkan current and then mau counter back there. That induced EMF must be in the same direction. That's why back EMF ni pun direction yang sama dengan original. So this one is after kita change the current. So color pink apabila kita change current tu dia akan still go in the same direction. It is the same concept macam yang tadi lah. So, tapi this one in terms of solenoid. Tadi tu in terms of coil and conductor. So, the keyword here is when I increase, back EMF, same direction. When I increase, back EMF is opposite direction. Mungkin kamu boleh ingat, okay, kalau susah sangat mau faham, kamu ingat benda tu je lah. I increase, EMF opposite direction. I decrease EMF, same direction. This is the same concept we apply in the coil and conductor as well. Okay, boleh?
Boleh, Miss.
Boleh, Miss.
Okay, nanti kamu rasanya dekat dalam, let me see, dalam nota kamu. Okay, dalam nota tu ada explanation. So, try baca balik explanation tu. Benda yang sama lah apa yang Miss explain. Try baca untuk kamu fahamkan dengan lebih jelas lagi. I know this topic is actually really hard to understand. Miss pun take time juga untuk faham. Tidak semestinya first time Miss explain ni kamu terus faham kan. So, try to do your own reading and then ingat baliklah apa yang Miss cakap ni. Okay, so basically proses yang Miss explain tadi ni to produce back EMF ni kita panggil dia sebagai self-inductance. Okay, self-inductance maksudnya dia produce sendiri dia punya EMF. Bukan tanpa memerlukan bantuan daripada magnet. So dia produce sendiri dekat dalam coil yang sama. So self-inductance ataupun kita gunakan simbol L is the process of producing an induced EMF in the coil due to the change of current flowing through the same coil. Okay, it must be flowing through the same coil. There is no external factor. Okay, tiada magnet untuk situasi ni. This is what we call as self-inductance. Ataupun by definition, it is the ratio, okay, mathematically, it is the ratio of self-induced back EMF to the rate of change of the current. Ataupun kita boleh gunakan dia macam ni lah. So, induced EMF, self-induced EMF is equal to the rate of change of the current in the coil. So, this is the rate of change of the current. So, kita punya inductance akan sama dengan negative EMF divided by DI over DT because we change that current. So, negative here we can ignore sebab Lenz's law just cakap it is to oppose the change. Okay, and in in 5.2, EMF is also equal to the number of turn times with the flux. So, kita boleh gunakan this formula di mana EMF is equal to negative L di over dt ataupun formula ni. Li is equal to N flux. Number of turn times with the flux. So unit untuk self-inductance adalah Henry. It is a scalar quantity. And then self-inductance untuk solenoid dan coil kita ada dua formula yang berbeza. So untuk solenoid, mu naught N square area divided by length. Untuk coil, mu naught N square area divided by 2R. So depends kepada soalan. Kalau dia minta solenoid, kita gunakan this one. For coil, kita akan gunakan this one. Okay, so basically self-inductance ni, kalau dalam circuit, this one kita akan gunakan dalam chapter 6 nanti. Kalau dalam circuit, kita akan gunakan simbol ni. So this one capacitor, this one the resistor, right? So this is the inductance, this one capacitance, this one the resistance, this is the battery. So we use this symbol in a circuit. So apa function self-inductance ni? It is used to store energy in the form of magnetic field. Before this, we learned capacitance is to store energy, but in terms of electric field. This one in terms of magnetic field. And resistance is just to limit the flowing of current here. And then we call this as inductor. Okay, boleh ada soalan?
Tiada soalan, Miss.
Tiada soalan. Okay, kalau tiada soalan, mungkin kamu nampak lebih jelas kalau kita tengok example lah. Okay, so let's look at the example. Okay, let's look at example 2 here. Okay, given here a 500 turns of solenoid with a length of 8 centimeter, when the current in the solenoid is increased from 0 to 2.5 ampere in 0.35 second, the magnitude of the induced EMF is 0.012 volt. Calculate the inductance of the solenoid, the cross-sectional area of the solenoid, and the final magnetic flux linkage through the solenoid. Okay, let's write down the information that we have. We have number of turn, we have the length, and then we also given that the current increase, initial dia kosong, and then dia increase kepada 2.5 ampere in a matter of 0.35 second. And then the induced EMF 0.012 volt. First question, we want to find what is the inductance of the solenoid. Okay, inductance macam yang Miss tunjuk tadi ada dua formula. Satu, when we have E is equal to negative L di dt. Dan satu lagi inductance untuk solenoid, mu naught N square A divided by L. So we can either use this one or this one, depends kepada information yang kita ada. Okay, so if we are to use this one, because we want to find L, so E kita ada, DI pun kita ada, perubahan daripada 0 kepada 2.5, P pun kita ada. So we can use this one. If we want to use this one, okay, mu naught is just the constant value given here. And then N is number of turn, kita ada area. Okay, we don't have the area of the solenoid. We only given the length. So length ada, area tiada. So this one we cannot use. So we use the first formula. So E 0.012 sama dengan negatif. Okay, negatif ni just apa yang include lah. Sama dengan L. DI is final minus initial. So final 2.5, initial 0, and then 0.35 minus 0. Okay, DI over DT adalah perubahan dalam, sorry, it's not A. Perubahan dalam current. I final minus I initial. Why did I put A? Okay, I initial 0, I final 2.5 ampere. Okay, so dapat berapa?
(1.6) at exponent -3.
6.1.6
(1.6) at
at exponent -3
-3.
Henry. Semua dapat 1.68 eksponen -3.
Dapat, Miss.
Okay. Or we can also write it down as millihenry. Okay, dua-dua jawapan diterima. Okay, next one. We need to calculate the cross-sectional area of the solenoid. So area of the solenoid, kita boleh gunakan this second formula in order to find A here. Sebab kita sudah ada value untuk inductance. Soalan B. 1.68, wait, kat sini lah. 1.68 eksponen -3. Mu naught adalah 4 pi eksponen -7. Number of turn, okay, ada square, divided by the length is at centimeter ubah kepada meter. So area is equal to
4.27 at exponent -4 m
-4.
square.
-4.
Yeah,
Ya, Miss.
yeah.
4.278 exponent -4 meter square. Okay, and last one, we want to calculate the final magnetic flux linkage through the solenoid. Okay, so notice here, it says magnetic flux linkage. Maksudnya, we want to find, so this is magnetic flux. Kalau dia cakap linkage, mesti darab dengan the number of turn. This is what we want to find. Okay, so there's another formula yang Miss tunjuk tadi. We call it Lino. This one. So in order to find this one, we just darab L darab dengan I. And since dia cakap final, so kita gunakan current yang final lah. So here, the magnetic flux linkage will be equal to L tadi 1.68 eksponen negatif 3 times with I. Current dia adalah 2.5 ampere.
(4.2 times 10 to the power of negative 3).
4.2. Okay, what is the unit?
Miss yang 10 to the power of negative 3 pula.
Negative 3, this one.
Yeah.
So what is the unit for magnetic flux linkage?
Weber.
Weber, right? Okay, jangan lupa unit Weber. Dia bukan Tesla. Tesla is for the magnetic field. So magnetic flux dia adalah Weber. Okay, semua boleh follow? Dapat jawapan?
Dapat, Miss.
Dapat, Miss.
Dapat, Miss.
Okay, so kalau dapat, let's continue to the next one. So next one kita ada example 12. Example 12 is straightforward, so I'm not gonna explain that one. Example 13. So this one pun gunakan formula je, straightforward. So I want to discuss this example 14. Okay, so example 14 here. Suppose you wish to make a solenoid whose self-inductance is 2.5 millihenry. The inductor is to have a cross-sectional area 3 exponent negative 3 meter square and the length 0.12 meter. How many turns of wire are needed? Okay, so this one for the case of solenoid. We want to find the number of turns when L is 25 millihenry. Area is 3 exponent negative 3 meter square and length is 0.2 meter. Okay, number of turn ni kita boleh nampak dekat 1 LINO, okay, lino. Satu lagi, bila kita keluarkan formula untuk solenoid, mu naught N square A divided by L. Okay, kalau kita gunakan this one, we need to find the I. We don't have the I. If we use this one, we have the L, N is what we want, area ada, length pun ada. So we can use this formula here to find the number of turn. This one straightforward juga, boleh masukkan terus apa information yang kita ada. N square times with area divided by the length.
Is bukan yang constant value to exponent negative 7 kan, Mas?
Oh, this one. Okay, sorry. Exponent negative 7.
Lapan
8, 9,
2.06.
892.06. Okay, kalau kamu dapat jawapan macam ni, okay, you cannot leave your answer like this. Sebab number of turn ni dia macam dia tidak boleh ada point. Sebab wire tu kan dia berpusing kan, dia macam the loop. So tidak boleh ada 0.6. So if you have the decimal place dekat belakang, always leave your answer without that decimal place. So kita ambil saja number yang di depan without bundarkan. Okay, tidak perlu bundarkan. So add 9 to tens. If we have 892 point, contohlah 67. Okay, kamu tidak boleh buat 893 sebab 0.67 tu dia tidak sampai pun 1 turn. This one only for the case of number of turn sahaja. So always leave your answer without bundarkan dan without giving decimal place. So jawapan dekat sini salah. Sini 892 lah sepatutnya. Okay, semua dapat?
Dapat, Miss.
Dapat
Miss.
Ada soalan?
Tiada, Miss.
Tiada, Miss.
Okay, so example 12 dan 13 kamu boleh buat sendiri ya. That one, solution dia sangat pendek je and it's very straightforward. So you can attempt it on your own, 12 dan 13. Okay, so habis sudah kita cover untuk 5.3. 5.3 ni dia tidak banyak pun sebab dia bercakap tentang self-inductance sahaja. So before I end the class, okay, let's recap apa yang kita belajar tadi untuk 5.3. So 5.3 we learn about self-inductance. What is self-inductance? It's basically just a process producing an induced EMF by changing the current. That's why when we write down the formula, kita akan dapat we produce EMF by changing the current. So we will get the self-inductance. Okay, so formula yang kita boleh gunakan, first is this one. Negative we can just always ignore sebab ni just to indicate the Lenz's law. Ataupun kita gunakan this one, depends kepada information yang kita dapat. So for the coil, we use this one. For the solenoid, kita akan gunakan this one. Okay, so just as a extra information, inductance ni dia bukanlah satu komponen yang fix macam resistor dan capacitor. Inductance ni kita boleh buat sendiri. Okay, menggunakan satu conductor. Okay, menggunakan satu conductor and then kita lilit wire. Okay, apabila kita lilit wire, since bila current flow throughout that wire, dia akan create magnetic field. That's why inductance ni kita panggil sebagai, komponen dia kita panggil sebagai inductor, di mana function dia adalah untuk to store energy in terms of magnetic field. So this one kita akan lebih banyak gunakan nanti dekat dalam chapter 5. Okay, usually kita akan ada 3 komponen, sorry bukan chapter 5, chapter 6. Usually kita akan ada 3 komponen di mana kita ada inductor, capacitor dan juga resistor. Okay, so nanti kamu cuba hadam baliklah proses untuk menghasilkan self-inductance ni. So nanti dekat dalam nota kamu ada penjelasan yang kamu boleh cuba baca. Maybe ada certain orang bila dia baca mungkin dia lebih faham. Ada certain orang bila dia dengar dia lebih faham. So try to understand the process here. Actually proses dia sama je lah, kita akan apply kedua-dua law, Faraday's dan Lenz's law. Okay, so kita sudah habis cover 5.2 dan 5.3. Next class I will cover 5.4 dan 5.5. Ada 2 subtopik lagi untuk chapter 5. Okay, ada soalan before I end the class?
So far jelas, Miss.
So far jelas. Yang lain?
no minute.
Tiada, Miss.
Jelas, Miss.
Okay, kalau tiada soalan, I guess that's all for today. Okay, I will see you tomorrow. Esok pun akan ada Google Meet ya, pukul 11 sampai 1. Okay, thank you.
Thank you, Miss.
Thank you,
Thank
Miss.
you, Miss.
Thank you, Miss.
Thank you, Miss.
Thank you, Miss.
Thank you, Miss.